Okay, so vectors, we stick primarily almost exclusively to dimension two, even though it's a shame because it's really everything is pretty much the same in the dimension. But the rest of what we'll be talking about, is just limited to dimension two, so just as well. And that's the key is here is this is the reverse operation so the two main operations of vector algebra are addition and scalar multiplication, but it does not mean that we are just execute them and done with them. Sometimes we have to work our way backwards and decompose. Okay, just like by analogy, is like you have a composite function and you decompose it into pieces so that each of them is simpler. Okay, so similarly here, what has happened here is we chose two main, as we say, basis vectors. 1, 0, 0, 1. So the length is 1. They're pointing in the direction along the axis. And then we can represent any vector as a linear combination of those two. So 32 is 3 times 1, 0 in the red direction along the x-axis, 3 times the units, and then up to in the vertical direction. So these are the meanings of the components of the vector. So you don't have to think necessarily about the endpoint of the vector, but rather decomposition into vectors that are aligned with the particular directions, which is very much along the lines of what the way we plan to do it, have done some of, and that is if we were motion, we studying motion, we're looking at separate dynamics in the vertical and horizontal direction. Okay, so that's how you can decompose it. Naturally, sometimes it's better this way, 32, sometimes better the other way, 3 times 1 is 0 plus 2 times 0, 1. Okay, so which one we don't know, but we do both. Just in case. So that's the representation. So these two vectors then are given, the red and the red and the green, and every vector, no matter where you point, will be decomposed in that manner. This very simple idea, which you see right here. Okay, vector AB is A times the first plus B times the second. So these are so important that they sometimes have been given special names. They not only they're called basis vectors, but they're also given I and J as the name of the two vectors. Okay, so then AB is AI plus BJ. Okay, so here's 1, 4. 1, 4, 4, 1 is decomposed into 4I plus J. Okay, so they are like building blocks of vectors, and you just need as many of well, the first kind plus the second of as many as necessary. The second, some of them can be negative if you want to point in the opposite direction, and that's all there is. So these are the it's called the standard basis of the plane of our two standard. So basis vectors, standard basis vectors, and within the implication that there might be in the near future is the basis vectors that are not standard. Okay, so the standards are the ones that align with the axes, but that doesn't have to be necessarily the case because the main thing that we want from a basis is this representability. Okay, so every vector can be represented in this fashion, and then you can guess that it doesn't have to be necessarily perpendicular. The issue is algebraic. So algebra is what we require. So not geometry. Which means that if we discard geometry, we set it aside, it means that distances, angles don't matter. Okay, so which means that the unit could be, you can imagine that if we would choose those basis vector be longer or shorter, it makes no difference. Still, the plan will work out. And then secondly, even more interesting is that the angle does not have to be necessarily 90 degrees in order for this plan to work out. So if this is I, if this is J, then you can imagine that instead of having a rectangle of red, that comes from Cartesian system, you can plot, you can have like this, like a grid like this. Okay, it still works out in exactly the same fashion, and so every vector can be represented. This is what we really want. We want to, if we want these vectors to be the building blocks, then every vector should be representable in this fashion. And then, like I said, distances, lengths don't matter, angles don't matter. Okay, so as long as the length is not zero, and as long as the angle is not zero, so that's the only. It cannot be equal to zero, and this cannot be equal to zero either. Otherwise, the plan doesn't work out. Okay, so you have two vectors parallel to each other. Naturally, you're ignoring the vertical direction, so it's not going to work. Okay, so Cartesian system is the axis, okay, for the points, and then the Cartesian system is the origin remains, but now we're not looking at the axes anymore, but the basis vector, like these two, red and gray. Okay, so all right. Okay, so here's how the choice of axes is how it comes up in some kind of basic physics. So if you were to study a motion of this object on an inclined plane, then there is a natural directions, horizontal and vertical, and the match is vertical is especially important because that's where the gravity is. But the horizontal is not so important because the motion is limited to the slope. Okay, so then it has got the object can only go this way. So in fact we have only one degree of freedom, as a matter of fact, and that degree of freedom is along the slope. So why not take these standard bases and replace them with something else, with one of them going along the slope. Okay, so why do I choose the perpendicular, and then the other one I still choose the perpendicular rather than the vertical, because that's where the resistance is. Okay, the resistance, the part of the gravity that is being canceled by the resistance of the slope is perpendicular to the slope, and then as you can see, the red part and the purple part is actually part of the gravity that actually does affect the object, and that is the purple part, as you can see, is what drags the object down the slope. Okay, so as if that's your choice, if the slope is actually the same, so throughout the motion, then this is a smart way of choosing your axes, your other basis vectors, rather than not axes but basis vectors, and you choose once again not necessarily a line and give it to you vertical and horizontal. Well, let's not. And let's choose these once again. One vector is along the slope, the other one's perpendicular, and the things work out much. The mathematics would be much easier. For one, it is entirely now one-dimensional, right? So the motion will be one-dimensional. So this is the purple vector is your direction along which the only anything is happening. Okay, nothing is happening in the other direction. So that's a smart way of analyzing something. Okay, so just an idea of why we keep an eye on the possibility of having other choice of basic vectors. Okay, so we'll see more and more reasons to do that later, but this is basic physics. Okay. Anyway, next. Okay, so let's now take these vectors and see what it has to do with systems of ordinary differential equations. So systems of ordinary differential equations, first of all, let me be clear, system of ordinary differential equations, okay, more than one. Okay, so x prime is equal to f of xy like this, and y prime is equal to g of xy. Okay, this is autonomous system of differential equations. Okay, just once again, if you have any doubts about where they come from, think about first about motion, an object thrown forward with vertical and horizontal direction independently changing, and secondly, predator-prey model. Okay, so where x and y are some foxes and rabbits. So that's a system on one hand, and then it is the same as a vector for dE. Okay, so singular. Okay, so if I want to write it, I would write it something like x prime is equal to f of x. As you can see, I capitalized everything. Why? Because all of these are vectors. Okay, so I have x prime, and this is not new to us, right? X prime, what is x? X is, what is x? In this context? Well, like I said, I'm saying that, well, you don't have to guess. I'm saying that these two things are the same. The system already is at the top, and then at the bottom, I have written this one single equation, but I call it a vector equation because everything that we have involved are vectors, and specifically, you can probably think of an example where x is what do we call it? What do we call it? Is it a vector really, or is it what? It's not a vector because otherwise I wouldn't have x prime. What's x prime? X prime? Okay, what about this prime? You know what this prime stands for? Or change, well, yeah, sure, change, a rate of change in the x direction, then rate of change in the y direction. So now x is the rate of change in what direction? In no directions, all directions at the same time, because it's a vector, taking care of all the possibilities. Without choice, any particular choice of axes, which is what the first one requires. There's an x and there's a y, and then we're studying in them in that respect. Here, this one will work with whatever choice of axes you do or basis vectors you choose. This will work out just fine. You just need to understand that x is, on the one hand, it's a vector. On the other hand, x prime stands for the derivative. What do we call things that a thing that is, on the one hand, it is a vector, on the other hand, we can differentiate it. What is that? From calculus 2 and 3. Who's taking calculus 3? So what do you remember from calculus 3? The main topic, the very beginning?
Partial derivatives.
No, okay, well, maybe that's the way it happens. So, okay, then what's the last topic in calculus 2?
Series. Well, that's what I did. Count to. We ended up.
Right. Well, I was writing at parametric curves, which I consider simpler than, say, functions of several variables, and they're on topic here rather than part functions of several variables, which requires partial derivatives, and so we're not doing that in this course. So it's a parametric curve, which is nothing special about it. It's a function, say, from t to x, okay, which is nothing but xy. Okay, so it's a vector, a time-dependent vector, where you are, which could be a location, so in that case could be a point, but definitely when you do differentiation, that is definitely a vector, because the derivative will be the velocity, which is a vector. Okay, so you have a parametric curve like this, okay, going this way, and then you produce a bunch of tangents. That's the main thing that you get in calculus. In calculus 2 and 3 is a parametric curve, which is nothing but two functions. That what's at the top, it still remains. You have a function of two variables, and then you can differentiate it separately with respect to the two variables, producing those tangent line indicating the velocities, the direction as well as the magnitude of your motion. Okay, so anyway, but then once again, so as good as this is fine, but this is definitely better. Because why is it better? Because it is, for one, it will work in any dimension that you want. So once you adopt this idea of notation that doesn't have to be broken down into dimensions separately, so it's a vector differentiated with respect to time, and so that motion can be in dimension of 3 or any dimension that you can think of. it's still, everything will still apply. So naturally we do both. And so we go back and forth between the two ideas. Okay, so let's review. So why did we spend so much time in one-dimensional case? Because now we can think by analogy, and we are mimicking the one-dimensional case. Okay, so that table is almost one-dimensional, with a couple of exceptions, but the rest is the same. So we have an ordinary differential equation. Where does it come from? Usually it comes from numerical analysis and the model. The model produces a difference equation, which then with the limit, if you go this way, take the limit and you have a differential equation. And then you analyze in a number of ways, including attempt on the right, solve the equation analytically. Once again, we are in the same place in high dimensions, even though it is way harder. Then you do a theoretical analysis, even though it's way harder, but it still works out exactly the same way. So that's not a problem. We'll still have existence and uniqueness. Then we have quotative analysis, and you can see what we did not use to have is this part. This is new. Okay, so increasing, well, they're not only, these are also new. This is new and this is new because when you speak of a function of one variable, I have a picture right here. The ordinary differential equation is a bunch of slopes, and you're supposed to very carefully find a curve that follows them. Okay, so then you're drawing a curve on the ty plane, and okay, but what cannot happen? You cannot go back. Okay, so you cannot go back. You're always progressing with time from left to right. So when you go to dimension 2 visualization, it's different, and then we are moving through the space, which is in this case a plane, which means that the dimension of time is invisible, it's hidden. Okay, so then we couldn't go back as we did with the predator prey model, as well as you think about planetary motion. There is no particular direction that we follow, so we can go back no problem. And this, once again, this is also a picture well represents what can happen. So that's the thing about three-dimensional case that we address, is that there is a little bit more questions to be answered, but it's still the same story. So qualitative analysis will be also similar, except more complications because of the multiple dimensions. Linearization, once again, also will work out the same way, except it's more complex. It's more complex because, once again, once it's higher dimension, it's more complex. Okay, but once again, the most important thing are probably understanding of what the equation is in the first place, producing, in fact, maybe starting with this, always model, and from model to a differential equation. That step is really the most challenging. And then once you do the analysis, the understanding of what the solution is, and that's, once again, just as before, a function that is differentiable, that when you substitute into the equation, gives you the true statement, the two functions equal to each other. So fortunately, we can do it slowly and review things one at a time with every single step is familiar, except now it will be in a higher dimension. Okay. Oh, so once again, the model is as you can see, if you want to sort of do it context free and not having any particular model, but have one toy model if you prefer. This is what you see here, vector fields. That's why we have been reviewing vectors, because how do we represent the differential equation is vector field, a field of vectors. So every point has a vector attached to it. Okay, so and then we're supposed to follow these vectors. So just like in the one-dimensional case, we're supposed to follow the slopes. Oops, somehow. Okay. Then in dimension 2, we might go like this. Okay, so we have to follow those arrows in the same manner. So those arrows are our tangent lines, just like in this picture. And then so we moving backwards rather than from blue, the function, to green its derivative. We were moving backwards. We're moving from the derivative to the function, and then it's not as easy as just to integrate. Okay, so that's what you probably do in calculus 2 and 3, when you can integrate parametric curve by just doing two directions separately, and then that's not much. It's just twice as much work, but there is no really challenge in terms of computations. So that this was not it's not as easy. Once again, this is if you wanna, if a vector field vector is still new to you, that this is the way to understand what's going on. Is imagine a field of on your lawn. There's a bunch of little flags, okay, and then they are freely to rotate depending on which way the air blows, okay, and then what you're supposed to figure out from it is actual paths, one particular of the airflow. So one particular particle of air, which way it's going to go through these flags. Judging by the way they're pointing, assuming that they're pointing the same way, then can you recover just the way I did it started over there? Can you recover the path, or predict the path of the object? So that's what differential equation is. So directions are given ahead of time, and then you're supposed to predict the motion. Okay, so the only difference is instead of one-dimensional, we have now two-dimensional. Okay, so you could practice yourself. So if I try to go like I start here, and then maybe like this, and then maybe it actually goes onto that dot. What is the dot? Is this stationary sequence? So maybe that's what it does. A path of that air particle will do that. Okay, so let's look at the discrete models. So that's remember that no matter how complex the model is, if we already have it, then we put it in the form of a difference equation. We have a recursive formula, and we can model it or do a simulation. Okay, so that's quite an advantage, a very good starting point. So it's not that only existing in your head, but rather it's a type here. But rather you can have something tangible. Okay, so this is a one-dimensional case right here in front of you, just to refresh your memory. So we are running through numbers that are sequence of moments of time, okay, which is just to keep count, because the increment is the same. And then the sequence of velocities that we acquire somewhere, okay, either it is provided to us, or it is being fed, or it's being computed. And then from the knowledge of velocity, we derive, although at this moment of time, we derive our next location. Okay, so that's what this is. So if you know, as you can see, delta t is our increment of time, and you multiply velocity by the increment of time, which gives you the displacement. This is the displacement, and then you add the previous location to the displacement to end up with your next location. Okay, so it's as simple as it gets. It is nothing but a table of values, and as you can see. So what's the difference? Now we have two of them. That's all there is. So at its simplest, then we have, we still have only one moment of string of times, but we have now two locations to the losses with respect to two different variables. That's it. And so the computations are then, if the velocity are given to us somehow, and then this formula still applies, but it applies twice. So vertical velocity gives you vertical location, horizontal velocity gives you horizontal location. That's all there is. So as you can see, I separated two into separate vertical pairs of columns. So separately handling x's and y's. Okay. So naturally, as I suggested some time ago when we started the topic, it is better to rather than combining x's with x's and y's with y's, which is right here, instead we combine locations with locations and velocities with velocities. That's a vector point of view. Okay, so look at it, the same columns, okay, but except now, as you can see, x's are here, x, y are here, these are locations. And then so location is what matters. Here we care about horizontal, vertical. Here we go location, velocity. Okay, so then it brings you to understand, then helps you to understand that it is locations are points or vectors, and velocities are points or vectors. And then you realize that it doesn't really matter. You can have as long as you adopt the vector approach, you can have two or three or four or five in each of these sets of columns, okay? It works out in exactly the same way. So that's why you study parametric curves, so you can differentiate a function, parametric curve, no matter what the dimension is. So naturally, in the back of your mind, you might remember that you do it as a differentiation of one component at a time. But here's I think I have it here, but it's not really. Let me write it. So limit h goes to 0, f t plus h minus f t over h. The definition of the derivative. Okay. Definition of the derivative from calculus 1 looks familiar, right? The derivative at t of function f, but here I intentionally I use the capital F, and then you might wondering what if f is in fact a vector. What difference would that make? And the answer is it doesn't make any difference. Why so? Because we have these algebraic operations on vectors. Therefore, whatever we're seeing here in the right hand side, as a matter of fact, makes perfect sense. So f could be a vector. And that would not make any difference because we can add vectors, we can multiply vectors by constant. So, so one vector is computed here, another here, then we subtract, and then we divide by a number, so which is also available. So if you can see that's the derivative of a parametric curve, and then all the calculus then can be redone for parametric curves. So usually you kind of skip over that very quickly because it's almost literally every single thing from calculus 1 is repeated in this manner. So if you want to actually do it, you just replace not every, but capitals replace lowercase with uppercase, and then you just say, well, it's a vector. So you're not allowed to do what? You're not allowed to multiply. So the product rule, for example, or quotient rule are out. But well, good riddance, really. So, but the main thing is that still the derivative makes sense, the velocity makes sense, and then now in this course we turn it around, and naturally we're interested in our knowledge. If we know the derivative, let's find the function. Okay, so we're moving backwards as before. Okay. So let's examine some of the examples of vector fields and what kind of dynamics that might produce. Okay, so here. More okay, so the velocity of the flow is proportional to the location for both horizontal and vertical. Okay, so that's maybe how I would write if I did not know vectors. I would write say u is equal to kf. So I have x and y are vectors. It is the location, and then I have uv vector is the velocity. And then if I were to take the model, so once again, let's carefully read the sentence again. The velocity of the flow is proportional to the location. So farther away you are from the center, from the origin, the faster you go. Okay, so then assuming that the proportion is the same, you write simply as u is equal to k x and v is equal to k y. Okay, so that's how you can do it if you do two separate analysis separate. So let's do it anyway, just for practice. What if we don't know vectors? How would we handle it? We would handle x and y separately, and then the vector field on the x-axis would look very simple. It will look like this. So when the x is 0, I'm not moving, and then let's say k is positive, and then like this. We've seen this before. Okay, you see what the picture here is it clear? So nothing, then it's 1, then it's 2, then it's 3, then it's 4. The farther away you are from the origin, the faster you're moving. And you're moving away from the origin. Okay, and then for y, it's the same picture for y, right? Like this. Once again, faster and faster you're moving away. Okay, so this is your horizontal motion, this is your vertical motion. Now, what is the combined motion? You can test, and once again, the answer is pretty much the same. The faster you're moving, the farther away you are from the origin, the faster you're moving. The faster you're moving. And every time that's what is not entirely clear. that, what is the direction of your motion? So, okay, so from this, it might not be entirely clear. So, let me zoom in on this. So once again, the horizontal and vertical, so this is my location, XY location, and what UV is velocity, okay? So I have a location, I know location X in the horizontal direction, then I multiply it by K, and I end up with the velocity. Okay, so the end result is this kind of a flow, accelerated flow. The farther away you are, the faster you're moving. Then you do the same with Y, and it has the same exact pattern. Okay, so the question now becomes, if you were to combine them together, these two dynamics, what is the dynamics? You still can describe it in the same fashion. So the farther away you are from the origin, the faster you're moving, but the direction is not entirely obviously present here. You can actually, the direction is, what is the direction? Which way are you moving? Faster, yes. But, and then you can still say faster on the XY plane, but that's not enough. So the farther away you're moving faster, but now it's unclear what's the direction. I'm here, that's the origin, say, and I'm located here. Okay, which way am I moving?
5 degrees of K is the same for both X and Y, right?
What if I'm here? And, okay, so how do you describe that motion? Like this? Like that? And if I'm over here, I'm moving up. So first of all, how do you know? How do you know that it's moving? Well, first of all, it is fairly easy to describe. If you wanna, the direction, how would you describe? And I would say away from the origin, right? That's what the picture shows, and then and that's quite what you want to say here. So if you're moving exactly, so my origin is right here, and that's what I want to. By the way, we're not even trying to solve any differential equation yet. We're just trying to create a model, and the model is a vector field. Okay, so that's my vector. I just to try to figure out what it looks like based on our description. And so once again, I decided to go first with a separate coordinates. X and Y, and then combine them together. And as you can see, there are questions to be asked here. So I'm moving faster and faster the farther away I'm from the origin, but which way maybe not entirely clear. If we go with vectors, that's alternatively. So one way is this way, and another way is this way. Okay, so look at it. The advantage is now we are speaking of vectors, and so if we are at the point X, Y, our direction, this is my velocity, this location, once again, this is my velocity right here. So it is equal to it is proportional to vector xy. Okay, so once again, if I'm at the origin here, it doesn't matter where my location now is. So this is the origin, this is my point xy. Okay, so I take my vector xy, this is my vector xy. Okay, and then what do? Yeah, I actually, I have to reattach it. I have to reattach it to the point xy. So that's what I do like this. So this is vector xy. This is vector xy, which is from the origin to xy. And now I take that vector and translate it forward to attach it to the point xy, which indicates not only where I am, but also which direction I'm moving. And because it's parallel, that's a parallel translation. I'm indeed moving away from the origin. So why so? Because that's what the multiple is. So there's a vector xy. I multiply by say by 2, whatever that is. And so then what happens to the vector if you multiply by 2? It's the same direction, only the magnitude has changed. Okay, so that's the advantage of thinking in terms of vector to begin with, right? Then one direction at a time, you are getting answer. If you understand vector algebra to begin with, that's right away you know what the way things are working out here. Okay, so okay, so that's roughly what this is. So the model is now has been created. That's my vector field. Vector field is right here. Vector field. Remember what vector field is it's a function from R2 to R2. Every point xy is supplied with a vector. So in a specific way, and we have a formula right there. Xy, the input, 2xy is the output. Okay, so that's a very specific formula. Naturally, you can write it out as, you know, like you can write it like this, 2xy, if you prefer it's the same thing. But that this notation hides the idea of stretching the vector. So the vector xy is multiplied by 2. So that's notation over there is better because, yeah, so it reveals the geometry of what's happening to the vectors, and that's how we know what the direction is. Nonetheless, so we stop here, and so appreciate that the model has been created now. We can derive some idea of what the dynamics is faster and faster as we are moving away from the center. So now we are at the next stage. So that if you like, you can say it's a qualitative analysis. Remember, qualitative analysis, that's supposed to indicate the direction, rough description of the motion, and the description of the motion is very predictable. As I say, it's well, maybe it's an explosion. Maybe, well, it's not an explosion. Why is it not an explosion? Right, yeah, I would say that when it slows, it moves faster than it slows down. So it's something else. Can you think of anything that moves like this? A motion that is actually moved faster as you move away from the center.
A rocket.
Oh, okay. Well, once again, think about a natural phenomenon. Why so? Because it's not never one rocket; it's a bunch of rockets. So if you look at the pictures that we have here, it is every location has its vector attached to it. So and so it whatever is moving through this thing through the vector field does not have an internal power source. It is in the flow. So there's there got to be some kind of phenomenon that guarantees this motion. So either flow or maybe forces in some kind. So there's something unnatural about the environment should accelerate the object. What could possibly accelerate the object?
It would look like that if you had like a fountain that put water up through a cone.
Right.
The farther it went, the faster.
And the well, because of the yeah, it's in fact, yeah. So how about a cone? It doesn't have to be a cone necessarily, but if that's a good example, or have a fountain. Okay, and then roughly what happens as the water flows out starts slow with 0 pretty much, and then because of the gravity it accelerates, so that it moves faster and faster, and then what we're seeing here in the picture that we had before is a view from above, view on the fountain from above. So once again, 0 at the center, and then slow, faster, and it directly away from the origin. Okay, so a fountain indeed. So it could be straight and it will be accelerated anyway because of the gravity. If you want to accelerate faster, you give it a different shape. So having said that, so QA is finished. Now let's actually do a simulation. Okay, so fortunately the two derivatives are separate from each other. We have our difference quotient right here. There's a difference quotient. I have my recursive formula. Okay, so xn plus 1 is equal to xn times x plus xk. Okay, so let's say maybe it's k is equal to 2, or let's make it small number. And then you can do x and y separately. Here it is. So that's literally what it happens. So we have to model 2 points rather than 2 directions rather than 1. But other than that, as you can see, that this is like an animation almost, how one particle is moving, and then you can totally see, first of all, that it between the blue is current and red. The next one, you can see how the distance every time gets longer and longer because it's accelerating. And secondly, look at the direction, it moving away as we anticipated, moving away from the origin, very much straight like this. Okay, so that our predictions have been confirmed with the simulation. I actually run it twice for 2 different starting points, and in either case we see both acceleration and as well as direction that points away from the origin. So once again, a fountain seen from above, if you like. So just like with other examples, it's even though we try to say we want only to trace one particle, but actually the picture is all the particles, and you see how they're flowing down that column. Okay, so that's the plan, the simplest model, simplest simulation. And qualitative analysis were also simple, and so we were going to do pretty much the same thing as necessary. Okay, so model two populations growing independently at the same rate. Okay, two populations. So we already have had a more complex example than that. We had predator prey. So two models, two populations interacting with each other. Okay, so that's why we have had a complicated model and complicated dynamics. So X and Y. So let's quickly remember that, because I expect you to know the answer, except if there will be two answers because there are two populations. So how do we write it? Population growing at a given rate. What's the differential equation?
Y prime equals Y.
Y prime equal Y, or let's be clear, by the way, differentiation is with respect to t, not x, and then output coefficient. Say x, kx, and say my. Okay, you see how the x and y do not interact. Okay, there is a k and m. Let's say they are both positive, so they are growing, growing. Okay, but also independent of each other. So they will be entirely. We can solve these two separately altogether, and as if they have nothing to do with each other. They don't. So the problem has been solved. But I want to nonetheless produce the vector field. What does the vector field look like? So the vector field, what is the vector field? It's the right-hand side of our equation. Okay, so this is the vector field. Okay, so kx is the first component, and y is the second component. So xy is, at every point xy is then associated with the vector. What is that vector? Kx and y. Okay, so
So if they're growing at the same rate, would the constant of proportionality be the same?
yes, but I'm not saying they're independent, right? So the proportionality, if you would say two identical populations, naturally they're growing at the same rate, but these are not identical populations. They could be still rabbits and foxes. They just happen not to eat each other. Okay, so they're living in different locations. So then they're growing naturally at a different rate, not the same rate. And so the logic that we have here disappears now, right? Because so what difference does that make? So instead of having, as I did over here, kxy, kx, ky, which happens to be kxy, right? Which is literally a stretch of the vector xy, and therefore the directions like we just saw, pointing away from the point, so leaving the origin behind. What about here? What's the direction?
Depends on where in X and Y are, so it would make a curve as you follow it.
Right, yeah, so it's not gonna be a straight line anymore. So best we can say that, well, let's pick specific points, say x, two x and y, how about this? So I'm choosing k equal to 2 and m equal to 1. So what does the graph look like? And so the ability to sketch vector fields becomes quite important. So if I have my point, so at 0 is still 0, so the 0 population will produce no growth. Then I'm having a picture over here that is very familiar. So the growth is 1 and then accelerates. Okay, like this. That's one of the population. The second population does the same, only slower. Okay, so like this. maybe not as fast, but also accelerates away from it. Okay, but it's because they're not aligned with each other with the same coefficient, so the growth will be well, maybe like this. Okay, so if I say take 1, 1, at 1, 1, the growth will be 2, 1, like this. As you can see, it's not, I'll quote 1. I think that I don't want to do the whole thing here. So the point is, the current population is 1, 1. Which way is it going? It is going in the direction 2, 1. It's not going in the direction 1, 1. It's not going in the direction 2, 2. So it's not going at 45 degrees because the population is growing at different rates. But it's going in direction, in this particular case, it will go direction 2 and 1. Okay, so in other words, it's not leaving the origin behind. It is somewhere behind. And indeed, if you start plotting, you do not expect this to be a straight line. Other than these are straight lines, right? So if the other population is absent, then of course it's straight line. Otherwise they are growing in different rates, and therefore they will be curving. Okay, so at some point we'll probably carry it out. There is an example here somewhere. So okay, so actually, okay, I see what we're saying. At the same rate, and here is not the same rate. If it's the same rate, then the picture is indeed what we just had. This is population growth, right? So look at our equations. This is the one we started with. But what if the rates are different? Then we end up with a kind of more complex behavior. So we'll model it later a little bit. Okay, so the horizontal velocity is proportional to the vertical location. Okay. The horizontal velocity is proportional to the vertical location, and the vertical velocity is proportional to the negative of the horizontal location. So these are actually two. These are not separate ones. It is the same. So these are taken together. So once again, if I just plot a couple for you, you will get what this is suggested to guess. So if I'm at 1, 1, for example, I have so it's 1, 1. The location is 1, 1. Which way am I going from 1, 1? And the answer is so my horizontal velocity is 1. Velocity is 1, so I'm moving. Hold on, that's 1. And the vertical velocity, that's horizontal, and the vertical velocity is -1. Okay, so the net result is this. Okay. So I'm not moving away, even approximately away from the origin. I'm circling. That's what the model produces, and so it's certainly not about population or anything like that, but it is about rotational dynamics. So you will be circling around the origin if your populations interact in this kind of weird way. So if you want to think of these not as motion, but rather motion through space of, say, populations, and so once again you have two populations. So the if you like, this is population 1, this is population 2. So the rate of growth of the first population is proportional to the number of the second population. Okay, so that's what the first line says. And so if they are kind of interact in this kind of negative way, then yeah, they will start rotating, except does not apply to populations, but rather that's why it's not about population, because you cannot have negative population. So this so the interpretation is really not as well applicable. So if we do not know, well, let's just carry it out. If it's unclear and you don't want to plot the vector field, it's probably a skill that you use in the future. So let's go straight with the and look at the simulation. Okay, so x prime is equal to well, actually, let's do a quick first. Let's do a quick qualitative analysis. So 4 quadrants. Okay, so xy here, x positive, y positive. Here x positive, y negative. Here x negative, y negative. And here x negative, y positive. Okay, so now according to the convention that we have here, then this is in reference to y prime, and this is x prime. Let me just rewrite this. So, okay, so let me take the first x positive, y positive, which means that y prime is positive, x prime is negative. Am I right here? No, the other way around. Y prime is positive, which means that x prime is positive too. Okay, and then x is positive, therefore y prime is negative. Okay, right? You see, that's so once again, I'm taking the first quadrant when both x and y are positive, which means that not only one vector you can do, I did it over there, but rather let's take all x and y's and let's just understand which way things are going. And so x prime is negative, x prime is positive, so they will look like this roughly. In the first quadrant, the direction will be roughly like this. It doesn't have to be 45 degrees. It varies depending on the location, but it will definitely be going downhill like this. Okay, and then if you carry out this plan several times, so for example, here I have y prime is negative, x prime is negative. Okay, so both x and y are negative, which means that this will be the direction of the motion roughly. So that, remember, we did qualitative analysis, we had a very crude idea of the direction of the dynamics, and that's what we see. So in the first quadrant, everything kind of going this way, that way. In the whatever that's second quadrant going this way, and then you will build some more, and then you combine together. That's you discover that that's your qualitative analysis. Okay, and then so that's if we want to do it in that order, so that's what we have. And then after you have the qualitative analysis, we skipped yet for now the theoretical analysis, existence and uniqueness. Let's just go straight to numerical analysis. As you can see, it's not so easy. Look at it's not so easy because now x and y's are mixed up. They're mixed up, so it's not going to be looking like an explosion. So modeling is producing the formula as one would expect. K and M are different rates, so they don't have to be the same. And indeed, if you look at the several, that's one simulation, 1 point from blue to red, then again from blue to red, and then that's you can see it is circling. You can actually guess what kind of a circle what kind of shape it follows. It doesn't look like a circle, does it? It looks kind of flatter, so it's probably an ellipse. Right, so you can see that it goes wider more than it goes, well, am I right here? No, it actually looks like, why does it look like a circle? So it crosses here at 3, and then over here at the bottom, it reaches 4, right? So it actually kind of elongated this way a little bit. Right, so horizontally it crosses the x-axis at 3, but it crosses the y-axis at -4, which means that it is elongated a little bit. And where did it come from? It comes from the misalignment. Equal K and M are not equal to each other. And in fact, if you zoom in here, they should be here somewhere. It's here somewhere. I don't know. Don't see it here, but it must be. Maybe it's 1 and 2. It's possible. Or maybe it's R. What's R? I don't know. Well, anyway, so the quality of the simulation is fine. It looks okay. It is circular motion, circular, but not circular, but rather cyclic. But it's not circular. It appears because of the lack of symmetry is what I'm saying here. X and Y are not interchangeable, right? So which means that you don't expect to have a circle. So anyway, once again, qualitative analysis, simulation, so everything will work out exactly as in dimension 1, just more stuff to happening, at least as twice as much, probably more than twice at a rate problem. So any questions about this analysis? Okay, so to go here, once again, you can modify this analysis, both the qualitative analysis and simulation very easily. So for example, two competitors with one success pushing the other one down. Okay, so that's one possibility. They're direct competitors. Or you have two allies with one success elevating the other. Okay, so one of these will be applicable. You can easily, once again, write x prime is equal to something that depends on y, and then or vice versa. Okay, so you can predict probably it's just a differently sounding models, but they produce always mathematics. They're way less mathematics than the things that you can describe in the world. So you were bound to end up with the same answers frequently. Okay, so, all right, so let's look at the, once again, at the, difference quotients and difference equations. That's this one. You take the limit, you end up with two derivatives. And then, so that's our main point of view. Once again, two, separately seen derivatives, but nonetheless, they're intermixed, so you cannot look at it, if you look carefully, x and y. So the rate of change of y depends on x and y, and the same with the dx dt. So we cannot split them. We cannot separate x's from y's. It's a miracle when it does happen, and that's, remember. So for example, an object rolling forward, that works out, but only because there is no horizontal force. Okay, so if it was, for example, air resistance, for example, then we would not have this luxury of solving two problems separately. And then finally, here is the vector idea. Vector, same thing expressed in vector notation. Okay, so f and g, that's the vector field. That's the vector field on the right. So two functions, each of two variables, each of which f gives you the horizontal, g gives you vertical, and that's a vector. And for each x, y, you have those two numbers. Those two numbers give you the vector. Okay, so once again, the picture, if I'm at x, y, this is my point x, y here, and then a vector has components f of x, y, u of x, y. And then somehow, so that's just a setup. This is just a setup. And then somehow you're supposed to actually find, you do this for every point of the plane, and somehow you are supposed to find the actual path. The path that follows these directions. Okay, so fortunately the challenge is not, so the answer is a primitive curve. And once again, you can think of it as two separate functions. That is being differentiated, then substitute. So x, you differentiate, substitute here, you take y, substitute over there, and then you're supposed to end up, that's what it means to have a solution, is it's supposed to produce identical functions on the left and on the right. Okay, so, and this is the simulation, just like in dimension one. Instead of doing one number at a time, we are doing one vector at a time. And so each of these is a vector, except for time. Time is still a number, but your velocity is a number. We multiply by delta t gives you the displacement, and then locations are also vectors, and so that's the vector algebra gives you a sequence of locations, just as you see here. Or that's a sequence of locations. Okay, so, all right, so recursive formulas, there are two recursive formulas, just as we saw over here. You don't see, I don't have the table here, unfortunately. So once again, remember what this is. So either top or bottom, it's the same thing, only with the rearranged columns. And once you click on, and another advantage of the vector approach is that you highlight this, click insert chart. Okay, so if you do it, if you do this, you would do this. You have to click, highlight these two columns and then click insert chart, and that will give you a path. So that one is slightly easier because the two are aligned with each other, next to each other. Okay, what else? Okay, so that's where we are. This is simulations. There's two formulas. Naturally, Excel, if this is all done with Excel, it doesn't understand vectors. So every time we might think in terms of vectors, but we have to for computation purposes, we have to break them into components. Okay, time, space, difference quotients, once again, okay. Taking the limit as a review, taking the limit of those difference quotients, we end up with derivatives, and that gives me the differential equation. By the right hand side is vector field, which is a function from R2 to R2, as I mentioned before, right here with every point on the plane is accompanied by a vector, which indicates the direction of the motion, direction and the speed of the motion at that location of that particle. If you are here, this is where you're moving, okay? All right, so let's see this, and then let's write it out for the record, what it means for a parametric curve to be a solution. And that's my system of differential equations. So once again, I could set the vectors aside for a moment. And then, so that's what it is. I take my x and y, two functions that better be differentiable. So that I have x and x prime, y prime. And so I compute them. I put them into my equation on the left. And then I substitute my x and y directly into the right-hand side functions f and g. And these two functions have to be equal to each other. Okay, so examples of solving are multiple. We already did one with motion. Remember, horizontal cannonball flying through the air, and you do them separately, but that's not always the case. So, for example, here's a differential system of differential equation right here. Okay, so that is where, for the first time, we really encounter a challenge, a computational challenge, even though each of them kind of looks similar, so simple together, it's not so simple. Okay, so how do we actually solve it? This is a totally solvable system, but the trick is so not obvious. Okay, so we want to solve it. Okay, so we know that we really only can hope for a stroke, a luck that goes our way, and then we can figure out how to solve. We just in one dimension was just a part. But here, once again, how do you separate x? How do you separate x and y? You cannot. So anybody see the trick here? How is absolutely unclear unless you know the trick. Well, it's not a trick. It is in fact a kind of, you can figure it out eventually. If the hint is eliminate. What do we eliminate? Okay, how about I tell you what we eliminate. We eliminate one. Can we eliminate one? I mean, it is after all, it is an equation, and then it is a strategy that you always have in mind. When you solve system, you have two unknown variables, then try to get rid of one of them. Okay, so you see how? Anyone? So anyway, so before we actually solving, there are experiments here. So a trial and error is a good idea after all. And so as you can see here, I'm trying x equals 0, y equal to 0, substitute them, and I have a bunch of solutions right away from nothing but guessing. So x prime, if derivative function is 0, then derivative is 0. So I have marking here. So these are all solutions. I try exponential function, right? So you have to recognize that there is something about I'm not sure if you see that there's an exponential, something exponential about the equation that we have seen is this. X prime is equal to x, right? Remember that one. So that one looks a little bit similar, except the x and y are flipped. Okay, so maybe it's not exactly the same. But nonetheless, if I try the exponential function, it actually works out. So exponential function is for both x and y is also a solution. But if I try t and t squared, then the derivatives do not match. And that's a fail. Okay, so it applies exactly the same way. And so it's always a good idea to make sure that some of the answers are obvious, some less than obvious. So how to solve it, we'll see later, but ultimately the keep always in mind, it doesn't matter how you solve it, what's the method is, what the trick is. Ultimately, it's about substitution, and the substitution either fails or it succeeds. And so your task is to find the one that does produce. So this is good and this is good. The only problem, as always, is have we found all of them? So we found a couple. we may have find more. Can you think of more?
No.
Well, warm, yeah, but hold on a second, well, it is a fair trial, so I can see how that comes to mind. So cosine t sine t, and you can see that it is not, does not look that bad, so let's substitute, so x prime is negative sine, and y prime is cosine. Okay, so yes, you can see the match supposed to be y is sine, and here it is negative sine, unfortunately. The second one works out, x is cosine. So as you can see, we have a match here and fail there. One fail, of course, produces a fail, but nonetheless, you can see that there is something going on here. Just if the sign was different, the answer would be okay. So for example, to fix, if I were taking this, what the differential equation would I supply? So even though I failed, can I think of ODE for this solution? So going backwards, not trying to solve an ODE that we failed anyway, and instead we have this nice solution. Can we think of an ODE for it?
X prime equals negative y.
Right, x prime is equal to negative y and y prime is equal to x, and that works out quite well. Okay, so we already had it. Remember, we already had this ODE, and now we kind of already solved it, right? So remember rotation? That's the rotation, right? So that's the rotation. It gives the answer ahead of time. This one is different because of the absence of the negative sign. So doesn't solve itself as easily, but nonetheless, we can see that there is something going on there. So parameter curves. Okay, so okay, so this is how we substitute. We have the graphs. We follow the vector field. This is remember the autonomous. We're concentrating on the autonomous. I did not emphasize that. And so this is an autonomous system. No T. No T. No T in the right hand side. Okay, so if it is a flow, then and then those flags are fixed in time. Okay, so hypothetically, I could imagine easily that those flags move with time, and then that would be just more complicated, but no, maybe not deservingly variable. So we concentrate on the autonomous systems. So, all right, okay, so flows, and then autonomous system has this property that we don't care. We don't care. The shift will produce shift in time produces a new solution every time. So that's what we remember from dimension one, and it's still the case. Like this. Okay, so if we have one solution, the shifting it with respect to time will produce more solutions. That's why we don't want to repeat all of them. And when we visualize solutions in dimension two, we just plot them on XY plane. Okay, and the time is present implicitly. So it saves us. There are no hidden solutions that we don't see. They have exactly the same shape. And the only thing that may be missing is add time labels, remember. So if you actually know how we follow this curve, then we have to indicate when we are in each of these locations. So autonomous systems, solution is the same. Okay, dimension one is a typical one. Hold on, I have the same picture here. That's the initial value problem. Since we are kind of out of time almost, let me just suggest a solution to this system. The trick to eliminate y, literally substitute. So how? And the answer is substitute. We're gonna do this in detail, but I already suggested to you. Substitute the first one into the second. What do I get? I substitute the first equation into the second. What do I get?
Y prime equals x double prime.
Y almost. Now it will be x. It will be x double prime is equal to x. Okay, so yeah, so as you can see, then And then, so we eliminated one of the variables and we now have, one variable to worry about. Okay, I'll stop here and I'll see you next time.